For joining us today. Before we get on to the webinar, I'll just do a little bit of Timber Design Society housekeeping. Excuse me. So today's webinar is going to be about case-hardened steel fasteners and mass timber construction. And we want to give a big thank you to our sponsors, Rothoblast, MyTech, iBuilt, XLAM, Simpson Strong-Tie, Future Build, and TechLam. Without their support, we wouldn't be able to do all these webinars, so we have a big thank you to them. The next webinar that we'll have is going to be in February next year. We want to give you a bit of a break in January to let everybody get back into the swing of things. So on the 20th of February, we'll have a case study, LVL, the key to low carbon and cost-effective industrial warehouse buildings. If you have any other topics that you'd like to hear about, that you'd like to present, please get in touch. We're always happy to have your feedback, and we're always looking for new topics to disseminate to you. So on to today's webinar. We've got 3 presenters today. We're very lucky. We've got a bit of a different format than we're used to. So today we've got Bjorn Stankiewicz presenting. He is the Technical Director for Timber at ENGCO. He's a structural engineer with a background in carpentry and expertise in structural timber engineering and building physicists. In his previous role as technical manager at Timber Unlimited, Bjorn led the development of a moisture management guide for mass timber projects and collaborated on the new NZS AS 1720.1 standard. We've got Eric McDonnell presenting today, and he is the Director of Mass Timber at Homes, where he oversees Homes' global efforts in the mass timber space to ensure knowledge sharing and improve the quality and consistency of Homes' mass timber designs. Prior to relocating back to New Zealand, Eric led Homes' Portland office in the Pacific Northwest. Over the past decade, Eric has developed an extensive portfolio of mass timber experience, including over 35 completed mass timber projects. And he's actively involved in industry-leading research, along with the development of mass timber design guides and code development. Finally, we've got Felix Scheidmeier, who's the Managing Director for Rothoblast New Zealand, where he uses his background in structural engineering and business to combine technical expertise with a passion for problem-solving, innovation, and commercial acumen. Focused on advancing the use of timber in modern construction, and he enjoys pushing the Rothoblast team to provide solutions to projects that prioritize the use of timber while ensuring better outcomes for the environment and the client. Bjorn, Eric, and Felix will present on the technical note that they've written about case-hardened steel fasteners for the TDS journal. If you're a TDS member, you should have received a copy of that from Lisa a couple days ago, so you might have had a browse through that already. And this highlights the potential issues of hydrogen embrittlement in case-hardened steel screws, which under some conditions can lead to screws failing. The tech note explains the conditions required for hydrogen embrittlement to occur, how to identify connections with a higher risk profile, and provides recommendations on how to mitigate the risk. So I'll pass it over to them. They're going to explain a bit more about this tech note. Thanks very much.
Thanks, Emma, and kia ora, everyone. So the whole aim of this presentation today is to give you an entry to this journey and an issue that has been observed worldwide and is slowly making, unfortunately, its way into New Zealand construction industry, especially when it's related to screws and mass timber. So Eric, Felix, and myself will take you through this, and hopefully we'll have answers to all the questions after this. So we do this today in an unusual format. So we have 3 speakers. And we will be jumping in and out to certain slides. So Eric, if you want to kick it off, let's start into the presentation. So why are we talking about this topic, and why is it suddenly so present in New Zealand, and what are we observing? So we all have seen this on several slides before. Mass timber structures and ponding water. And then we have fixings, steel plates, screws, and those are obviously connected to the COT and glue limb members. And they are exposed to a lot of moisture. And excessive moisture obviously leads to corrosion. And corrosion, if a screw is damaged, can lead to hydrogen embrittlement in your fastener and ultimately lead to failures. So how do these failures look like, and what has been observed throughout the world at the moment is we see popping head of screws, and then on the other hand we see screws that snap at the intersection between, or the transition between, the shank and the thread, because we have a little step in the thickness of the diameter and stress concentrations. So when it comes to cracking, hydrogen embrittlement, we have to go to the anatomy of the screw, and Felix will guide us through that.
Thanks, Bjorn. So the important thing to understand here is that we're probably not talking about the standard wood screw that you might have seen in the past in New Zealand. So we're not talking about the small screws that you might pick up from Bunnings. It's the larger screws that you use in mass timber structures. Generally, we're talking about diameters of 8mm or larger. A lot of fully threaded screws or partially threaded screws, depending on the application, and then with multiple head types. So the head type that you can see in the picture there is just one example of, I guess, what's possible in terms of washer head, standard countersunk head, or specialised heads for steel plate to timber connections. So the fastener itself is made up of a core material that's generally a high strength but ductile material. That's very, very important from a design point of view, especially in New Zealand where we experience earthquake loads. And then on the outside of that, you've got a case-hardened section, which is achieved by, I guess, heating and then tempering or quenching the screws during the manufacturing process. And that gives you an increased performance in terms of your thread and your drill tips, and allows for correct installation and torsional capacity for that install phase. On the outside of that, you've got a coating, and all of these things will become important later on. So Eric and Bjorn will discuss, I guess, why you need to be careful in terms of which coating you're using and how that affects hydrogen embrittlement and the possibility of a screw failure. But the coating on the outside is a critical portion of that. Oftentimes we have zinc coating as a standard coating, or you may have zinc with an epoxy matrix over the top, or some kind of other organic coating that's possible as well for these screws.
Yeah, so what is a hydrogen embrittlement? I think what it is really the embrittlement of the screw with the introduction of atomic hydrogen into that core, which turns it from that ductile material again to a brittle material, and you could get early failure of that fastener. But it is important to understand that there's three things that all have to occur in unison for hydrogen embrittlement to occur. And one is to have a susceptible fastener. The fastener also has to be under sustained tension, and we'll kind of get into what that means. And then you also need the introduction of hydrogen into that fastener core. And that is typically, we'll kind of go into this as well, but that's typically either from free water or actually the corrosion of the coating itself. I don't know, Felix, do you want to talk to these two images here?
Yeah, I think, like you said there, Eric, the importance is the disruption of the metal itself that's caused by the hydrogen as it progresses into the structure. So whilst you start out with a ductile fastener, you can see on the right-hand side there in yellow the embrittlement. That's the disruption of the structure itself. That's a very rapid process, and it's something that causes catastrophic failure rather than the slow kind of ductile failures that we're used to seeing with these type of connection details. So the head's popping off. Generally, it starts with I guess, a stress corrosion crack, but realistically it progresses very, very quickly from that. And you can see that on the left-hand side image there, where you've got a very, very small starting failure plane, and then the large, very flat failure plane, which is an instantaneous failure of that fixing. So it's very unpredictable and happens very quickly. So it's something that needs to be controlled I guess, from the design and install point of view, and designers need to be aware.
Yeah, so in terms of what makes a susceptible fastener, one is the quality and makeup of the steel that's going into the core. I want to make sure you have good quality steel. The other is, how hard is that core? And what we kind of what's been outlined in this ISO technical report is really that below, if you have a hardness below 360, the risk to hydrogen embrittlement is pretty low, not eliminated, but certainly much lower. When you're above 390, it's shown that the risk can be starts to get quite elevated and increase pretty quickly. And in between 360 and 390, it's considered to be manageable if the right precautions are taken, which is we'll kind of outline what's outlined in the tech report. But the reason we can't have everything below 360 is just in order to achieve the installation and the structural requirements from the fasteners, they tend to need to be within this 360 to 390 range. So that's why we're working within that range. And then we've kind of broken down, and I guess there's really two different types of hydrogen embrittlement, which are the significant ones. And one is if there's hydrogen embrittlement introduced in the fabrication standpoint, and that's something that could be pretty well controlled and tested because you're in a really controlled environment. But even after that point, these screws now have to go out and live in a real construction environment. And so that's where we'll kind of spend the most of the focus on. But Felix will kind of take us through what we do from a fabrication standpoint.
So we make the distinction here between internal hydrogen embrittlement and later on external hydrogen embrittlement, and that's a very important one because the internal hydrogen embrittlement is really out of the control of the user. It's very much a manufacturing process. So the hydrogen is introduced into the material before it's released onto site, let's say. As manufacturers or screw manufacturers, that process can be managed during the production cycle. So, for example, by adding some inhibitors into the acid wash, by looking at how the electroplating process is done, and also then by doing some verification testing to check what, I guess, the level of hydrogen is, or to check that there's no initial failures. So you can see down the bottom there, it still depends on the fastener material somewhat. So you've got the hardness still coming into play here. When the hardness is under 360, actually as a manufacturer, you tend to not need to check for IHE. It's very unlikely to be a problem. As you go up from there, you start to see an increased risk. And there's ways to deal with that increased risk. So you can either, whilst you're between 360 and 390, so that mid-range, you can do a test, which is a sustained tension test. So you put a sample of that screw after manufacturing under tension for a period of time and check if there's a failure. If you then get a failure there, you would bake that batch and then retest it. If you retest it and it fails again, then that batch wouldn't be released, so you would essentially discard it. If you're above 390, then you're essentially always baking. The baking helps in terms of diffusing the hydrogen atoms, so it reduces, I guess, the concentration of the hydrogen atoms in certain parts of the screw, and allows for those screws to still be released or pass that ISO test. The important thing here is that, like I said, it is really out of control of the end user. It's something that the good manufacturers are doing by rights now. And if you had an IHE failure on site, it would manifest very, very quickly. So essentially during the install rather than afterwards, as with EHE, when you have external effects that have come into play.
Yeah, and essentially what you're doing through these tests is you're showing that there hasn't been any hydrogen introduced into the screw during the manufacturing process. But then now these screws, you may have shown that through the manufacturing process, there's no introduced hydrogen, but now these have to go live out in a construction environment. There's important steps to be taking during the storage of the fasteners to make sure they aren't exposed to moisture. And then, yeah, per this image here, often our job surface is quite wet, so that we have free water. And then there also can, if that sits there for too long and exceeds what the coating can do, you're also going to start to get corrosion of that coating, which could then introduce hydrogen to the core. So, in that environment, we know that the likelihood of exposure to hydrogen is going to go up. We know the likelihood of sustained tension is likely to go up as particularly if the timber is swelling. So that just shows the importance of trying to reduce the susceptibility of the fastener. And then we'll also go down through some steps to try and reduce the risk of the high sustained tensions and more potential introductions of hydrogen.
First drivers of the environmental hydrogen embrittlement is the sustained tension. And there's a bit of uncertainty around how much sustained tension is too much. So the decisions or the arguments are between 10 to 50%, but then excessive moisture gain can lead to unintended sustained tension on top of all the factors that we see in our design. And the designer needs to take into account all the influences that and establish the risk, really, right? So to reduce the risk as much as possible, we need to look into design tension force at the start. We need to look into the overtorque, which is happening on site at the installation. And then we need to look into the moisture that is occurring during the construction period and continuous wetting of the timber, which is leading to swelling. And if the swelling is resisted by a steel plate and a screw fixed into the timber below that is expanding, we increasing the sustained tension on the screw. So we need to work out, is this all lower than the design capacity of the screw? Well, that's the big question mark, really. And the way we can reduce these things as much as possible is to look into each individual of these items. So first of all, design tension force of the screw. We need to look at the connection type. Is it a connection that is predominantly loaded in shear and doesn't have any sustained tension in service or in construction loading? We reduce that risk already significantly. If we have a gravity connection, let's say with inclined screws, where the screws are already loaded in the construction sequence or even loaded more as we load things on top of the floor, we might actually get to the design capacity of the screw already in construction. Then we need to be even more careful with the other two items in this equation, which is the overtorque, where we need to make sure that the contractors are following the QA instructions from the supplier of the screws. And then it comes to the swelling, and this is one of the most critical ones. And we heard a lot about this topic, unfortunately, over the last year, and it is really again back to the point to limit and control the moisture on site. Or if you can't, and if you have to, let's say, put a drag strip or tension strip onto a mass timber floor where potentially moisture could get underneath it and get entrapped, then we might have to delay the install of a high quantity of screws to mitigate the risk of the majority of them rupturing during construction and allow for redundancy throughout the further process. So we need to answer this big red question mark at the end is we need to look into these individual steps and mitigate the risk. There is really no one equation where you can sum all the forces up and comply with a standard or a design capacity. You really need to look what the risk of the connection is in itself, and how the manufacturers specify their talking. Felix will say a few words to that.
Thanks, Bjorn. So as a both a designer and an installer, I guess it's important to understand some of the key drivers and what you should be looking for, and those you should be looking for from your screw manufacturers or your fastener manufacturer. So I can speak for the Rauterblast case here, but I know that certainly plenty of other manufacturers have the required information in their install guides as well. But in our case, you would look in particular now for steel to timber connections. Those fixings that are often used will generally have an install guide that will give you the maximum torque limits. So it's important to understand that that is the maximum. It doesn't mean that as an installer you have to aim for that maximum. It's the maximum that we recommend before you start seeing issues in terms of over torquing the screw and adding additional tension before you've even started with your connection detail. So you can actually work with much lower torque limits because a lot of these connection details are in shear, which means that as long as they're kind of snug fit, they'll do the job just fine. We'll give install tool guidance, in our case through the Smart Book for Screws, for example, or the install sheets for the HP's plate screws. You'll see tools and procedures that can be used, things that shouldn't be done, and recommendations from our side as to how the engineer, for example, should be checking on site if things have been done correctly, and some tools that we expect an installer to use. So it's quite critical that these are followed. And if we skip to the next slide now, Eric, there's some very good reasons behind that. So if we look first on the right-hand side there, that gives a little bit of an indication of a deviation in terms of angle when you're installing a screw into a steel plate. You can see that it becomes quite noticeable from 10 degrees. But what often happens is if the install guidelines aren't followed, the contractor will actually go ahead and just keep applying torque until that screw head sits flat against the steel, because then everything looks perfect and the engineer comes along and there's no problems. But what that means is that there's definitely an over torque in the screw, and it's likely that you've reduced the capacity of that screw below what the designer, I guess, intended in their design. If you look on the left-hand side, the other outcome there is that you damage the coating of the screw. So that's particularly important for zinc-coated screws, because at that damage point, you then get extremely accelerated corrosion, which will lead to failure of that fastener at a much, much lower capacity than is intended by, I guess, us as screw manufacturers and the designer, because the hydrogen embrittlement really does come in quite quickly then and can happen at lower moisture contents than expected. So it is critically important to use the correct tools to follow those guidelines, and I guess to understand that when we're installing these connection details, which let's call them higher risk ones, the steel to timber connections, that it is required to really follow those to the letter and be very aware of those install requirements that the manufacturers set out.
The fine tension is obviously also highly depending on the thickness of the steel plate. So in the construction in New Zealand, we're continuously increasing the demands and the specs of the houses and the projects we're looking at, and the steel plates are getting thicker and thicker. So what that brings along is obviously the steel plate its capability is being reduced to yield. The thinner steel plates on the top right, you can see some of the screw manufacturers have done some testing and found that using thinner steel plates, the steel plate will yield, and the sustained tension on the screw that is building up because the timber swells below is not as high as compared to a thicker steel plate, which is not yielding and obviously capturing more of the increasing and swelling timber below it. So when we look at construction sites, we have to look into fixing these screws into thick steel plates. Obviously need to be more cautious and more risk averse to the introduction of moisture and trapping moisture below it to reduce that. There are ways to add some layers in between steel plate and the timber if we cannot mitigate the risk of the moisture getting there. And in terms of a rubber mounting that will compensate for some of the pressure and dissipate this. Other options, obviously, to lift the steel plate and allow for some circulation of air underneath it to avoid the moisture increase in the timber itself, but more to that later. The main thing is really to look into the screw and to use the right screw for what we're doing with the moisture content that we're expecting on site.
So the next portion that we need to look at is the exposure to atomic hydrogen. So how can we reduce that, or how can we deal with that, and where does it come in? So in terms of potential sources, this can happen, I guess, during storage and during construction, depending on which part of the world you work in. And generally it's either free water or a damage to the coating or reaction with the coating, so essentially rusting of the zinc coating, and that then introducing atomic hydrogen into the core. When we say storage, that's particularly important for high humidity locations. So you can get that same kind of response if you store your screws for a long period of time in an environment that's not suitable for that particular fastener type. And we'll come to that a little bit on the next slide in terms of what kind of moisture content levels we're looking at there and what's allowable for each different coating type. The risk really depends or is project by project based. So as a designer, you need to consider things like the pollution that you expect in the air, the sea spray exposure that you expect, the timber treatment, which is very, very important if you've got wet timber. And understanding, I guess, not just what that building looks like once it's closed in, but what that building's exposure is like during the construction phase, which is likely the more critical phases out of the two. We can do things like avoid standing water, but again, particularly important for things like your steel plate connections that are put on your CLT floors, where oftentimes the water has nowhere else to go. So unless it's correctly covered, and I say correctly covered because it's not just covered by a plastic membrane, it has to be something that's highly breathable that lets the moisture out. But the water will sit under the steel plates, and it's very clear from testing that we've seen out on the building sites that around it might be completely dry. So the timber, if you're testing the timber, let's say 20 centimeters away, you get a great reading, but under the steel plate itself is still completely wet. So that needs to be taken into account from a design point of view as well, to say, okay, do we mitigate that by maybe installing that connection detail later, or covering it somehow with a breathable membrane, or looking at a correct moisture management plan to ensure that we can either mitigate or completely eliminate that risk. The other important thing is that depending on the fastener coating that you've got, it's very important to understand what the impact of damaging that fastener is. So particularly with zinc coated connections, once you damage the fastener, it does accelerate the process of corrosion. So as you're installing the fastener again, if you're in these high risk zones, more care needs to be taken in terms of monitoring the install and understanding if there's damage occurring. On the right-hand side there, just before we leave that slide, as an example that we have in our Smart Book for Screws, for example, where you can look at your atmospheric corrosion and your wood corrosion class, which is explained a bit earlier in that book, and from there decide on which coating you might want to choose. So there's some guidance out there in terms of helping you as a designer picking the right coating. If we look at moisture content levels and how we best design those, then really the latest iteration of the Eurocode, which is currently in draft, is the best place to look. Like I said before, we're not looking here at, I guess, the end use of the building most of the time, because generally when we're designing a standard timber building, we're likely to be in for the internal in service class 1. But we're looking at the moisture that's likely to be affecting those fixings during the construction phase. So oftentimes we'll be in that second service class there, and you can see there's some upper limits of 20% for the moisture content and yearly average limits of 16%. So what we're trying to say there is that really we want to be more around that 16. Those upper limits are just that. 20% is the very top of that range, and once you step over that into your class 3, you start to see some very or an acceleration in the corrosion that you get. This here's a reproduction, I guess, from some research that was done some time ago, but you can see that in terms of your corrosion rates, if you're in that roughly service class 1, so from let's say 1 to 12% moisture content, you really don't see any corrosion at all in your fixings, and there it doesn't matter as much if you've got treated timber or not. Once you're in that space, there's not much corrosion that's happening. Once you get into the service class 2, you do start to see a slight increase there, but again, it's reasonably manageable. But what's important to consider is that when you step out of that service class 2 into service class 3, the acceleration is very rapid. And you see that it accelerates until you've got your fibre saturation point in your timber, and then it plateaus out again. But between that kind of 20-odd% moisture content, 30% moisture content, your corrosion really does go through the roof. So it's important then to understand, okay, can I either stay out of that zone altogether by having a rock solid moisture management plan, or do I need to consider the fastener type that I'm using and maybe look at the hardness of the fasteners there, or do I need to look at the coating on my fastener to ensure that I'm protecting that core, and then also looking at the install and bits and pieces to go with it.
All right, and so back to the susceptibility of the fasteners again, sort of our third driver or ingredient that's required. Typically this is evaluated, at least for case-hardened fasteners like we're discussing today, it's evaluated based on the core hardness. And again, it kind of falls within these 3 risk bands. And we'll kind of go a little bit in sort of the leaders of this are actually the Canadians that have updated their code to address this. And it was sort of in response to a few failures that they had of fasteners at elevated moisture contents. And so, yeah, we'll go into that just a second. But I would say, there's really no other code out there that's really addressed this very well. It's not addressed very well in the Eurocode or the North American Code, which is the IBC. And I would say even the approvals for the fasteners, the ETAs or the ICC reports used in North America, and none of these really address hydrogen embrittlement. So right now, this new Canadian standard is really kind of the forefront and the one that we could look to. So I guess a few key things here is to reduce your risk is, we could start looking at specifying fasteners that can meet the new Canadian standards. There are a number of fastener manufacturers that could do this now, and there are a number of others that are looking to adjust their processes to meet this standard. And then if we can't, it's even more important to address those other two ingredients to reduce the risk. So this is an excerpt of the Canadian standard. And basically what it's saying is for service classes 1 and 2, they're recommending that the core hardness be below 390 Vickers hardness. And then there's also, if you're going to step outside of that into service class 3, they're actually recommending that the hardness of the core be 360 Vickers hardness or below. And I guess kind of the key here is this provides a greater margin of error, but it doesn't eliminate the risk. So it's still very important to looking at trying to control and mitigate your moisture. So again, these are the three things, 3 ingredients that you need. We know we're unlikely to eliminate any one of those in most cases, so we just need to reduce the risk as much as possible, kind of pulling all the different levers to get us out of this elevated risk zone. And Bjorn's going to walk us through a few of our recommendations that are outlined in the paper.
Thanks, Eric. So obviously to create a risk matrix to identify the high risk conditions is the first thing to do. And the first thing that we can use to communicate those critical elements to everyone involved, from supply to construction. And potentially we have to modify these connections based on that, as Felix mentioned, use different fastener coatings or even different fastener materials and or the time of installation as required. And then what we also should be looking at is what the Canadians have suggested at the moment and what McKenna has been used as best practice in the CSA 086 is that we should be looking at the boundary conditions of the risk is highly reduced below 360, 390 being the upper limit of the hardness. But then we have to also be looking at longer screws, as in fully threaded screws or connections where the connector potentially is not going to get wet on site or is exposed to prolonged wetting and therefore a movement in the timber. And in those cases, we potentially could be relaxing those decisions and specifying a more harder screw, which is ultimately giving us a higher design capacity, which we need to obviously consider as well when it comes to diameter of the screw and size, and therefore price and edge distances attached to it. But then obviously when it comes to that, we also need to look what the manufacturer and the supplier is recommending and is understood fully by the contractor. And that is going from time of the installation to the torquing of the screw, as well as using the right tools, as in pre-drilling if needed, using gauges to stop the screw from hitting the steel plates, and do not use impact driver when you use steel plates, which is a significant point to look at and has to be somehow be followed by the contractors on site and rigorously, stringently be checked by us as well as the engineer and asked for in the specifications as well. We need to ensure that the coatings are sufficient for inspected site conditions. Felix has walked us through this quite well, I find. Sometimes we go and see sites that might not be exceeding these conditions as we're building in summer. But if we know we're building in a wet season and we cannot maintain the moisture of the timber and the limitations and the construction sequence doesn't allow it, we might have to up the coating to a higher service class or even a higher material that is not susceptible to corrosion in these service classes. And obviously, coming back to that is a clear, achievable moisture mitigation plan. So don't go overboard with this. You need to be realistic. And one of the things that you can do and help everyone, and it has been done recently in several larger buildings in New Zealand already, is to install moisture monitors in construction already, close to those connections to identify and send alarms if the moisture content should be exceeding, and then to obviously initiate steps to mitigate the risk of the timber swelling and the timber actually drying out below these plates. And then obviously, when it comes to that, especially for us in New Zealand, high seismic demands, we will need thicker steel plates than most of the rest of the world. And therefore need to be looking obviously to how do we deal with those? Do we drop the steel plates directly onto the timber if it's just for diaphragm steel ties, or do we put some shim plates underneath to let air circulate under, install only a certain amount of screws that we require in construction, and then as the timber building is enclosed and the moisture is actually under control, we can lower these plates down, we don't entrap moisture, and we can install the fastener. If we have obviously shear brackets that also function in gravity, we will have to potentially put some additional propping in if we cannot ensure that the moisture is kept out of the connection, or design a redundant bolt or something for construction sequence that is obviously not susceptible to corrosion, hydrogen embrittlement. Nevertheless, core hardness, we talked about this, does not limit. That core hardness is limiting, it does not replace a moisture management plan, so that is always a risk. And the risk is mitigated by dropping the core hardness down, obviously, but we need to be really aware of what's going on and spread this this issue that we have observed worldwide over the last years to the contractor, and alert to them to follow the instruction of the supplier and of us engineers, specifying the right conditions for the construction. And with that, we're leading over to the questions and open the panel to Emma and lead us into it.
Awesome. Thank you very much. That was very informative and well presented. We've got a few questions here, and for anybody listening, please feel free to upvote any of the questions that you're interested in, or add your own questions as we go, and we'll get through as many as we can in the next 15 or so minutes. First question, is this just a problem when screws are under tension loads, or is shear on screws not a concern for hydrogen embrittlement?
I can probably jump in there. I think generally what will happen is with a lot of these screws, you will generate some tension with a certain level of shear, right? So the shear load in itself is not the issue, it's the tension resulting from, let's say, some of the movement that then happens with that shear loading. So the screw being in tension is the important part. The connection detail can be a shear detail, but you can still get tension in the screw, particularly with things like moisture content change, for example.
Yeah,
Or
and
installation, as you showed in the slides as well. Any installation issues, even if it's a shear connection, you could still end up with tension in the screw that you're not expecting.
yeah, that's right. But if you are able to control those other things, yeah, shear alone is not an issue in this case. It's just whether that shear induces some tension, as Felix said. The other thing is, a lot of what we're talking about with these thick plates, for example, typically those are seismic shear loads. So you may not even have any shear loads on that. And then it primarily comes down to, has it been over torqued or installed correctly? And how much tension is building up to the moisture content gain.
Thank you. Is IHE also applied to stainless steel screws?
I would say in general, no. So there's a little bit of a different process there. Stainless steel tends to react more if you've got something like a bolted connection where you've got two nuts on the other side and there's no air getting to the material in between. That's when you generally see the hydrogen embrittlement issues in stainless. So from a screw point of view, it's very unlikely to be your driver. It's also a softer material, so there's some other points to consider there, but I would say in the general answer, no, not the same as your zinc-coated screw.
Yeah, and I would say if you're looking to use stainless steel screws, talk to your contractor early, talk to the manufacturers early, because even though they're in the catalog, most stainless screws are not readily available. So if you haven't planned in advance for those screws, you may get to construction and the design or the construction team can't source them.
Thank you. I understand that screw head snapping off is a clear failure that can be observed in the immediate aftermath or short term of screw install. For fully threaded screws which connect two elements, there is a chance that stress concentrations exist at that interface. A failed screw in this scenario would be hard to identify. What risk exists for existing construction of fully threaded screws to hydrogen embrittlement? Are there any tests which can be done to screen existing connections?
So I think I'll go first, Eric, and then you can jump in if you like. I think the important thing to understand here is that if you've got a timber-to-timber connection, you've already got a significant decrease in the chance that you're going to get one of these failures. So unless you've got, say, a very, very high density LVL, like the ones that you get in Europe, up against a softwood timber, so a significant difference in densities, where you then get quite different movement or I guess tension generated as the moisture is applied. It's unlikely that in a normal timber-to-timber connection you'd see the amount of tension required to cause this type of failure, purely because the screw will move inside the timber as well. So the timber will relax around it and you don't get that high peak. The risk of existing construction, generally, once it's dry, there's no risk whatsoever. I say generally because obviously if you had a construction phase where you've left it outside for 4 months and you've got red rust coming off your screws, then yes, you will have a potential issue afterwards, but that's likely a completely different issue to hydrogen embrittlement in that case.
Yeah, the only thing I would add is your unintended tension in those fasteners is likely to reduce quite a bit as the timber's drying out. So instead of getting the swelling where you're getting this unintended tension buildup, you're actually going to get a retraction out of that.
Thank you. If screws are galvanized, that's to my question. 1 second. If screws are galvanized, could off specification pre-galvanizing acid pickling be a possible cause of hydrogen embrittlement?
Yes, it could be. So that's definitely part of the quality control process that a manufacturer needs to go through with their manufacturing plant. So it's very important that that during that manufacturing process, the correct limits are set. So as manufacturers, we quite closely control that process. So you shouldn't get, if you're going with a reputable supplier, you shouldn't get that situation happening at all.
Thank you. How long would environmental conditions have to be met to pose a risk of hydrogen embrittlement? Subtropics use mass timber and have a relative humidity greater than 85%. Should we be worried that all of our screws are snapping?
No, I think it's related to one important fact here, that the screw, if it's under tension and it has no microcracking of the coating and there's no hydrogen getting into the screw, you don't have this problem for a start. The other problem is if you use a screw with a service class that is not that shouldn't be used, and the timber gets wetter than you have allowed for, then obviously over time you would have to look for it. On site, we experienced the screws between 2 and 3 months being prolonged exposed to moisture and therefore excelled to another service class. That process, just because of relative humidity, takes a lot of time. And unless your screw is compromised, damaged at the install, it is highly unlikely that you get there. But you would have to obviously look into if you worried about certain critical connections, check them definitely. But I wouldn't say that all the screws have popped right now just because of that.
Have there been any major failures or fatalities due to this happening on any projects that you're aware of?
I'm not aware
No.
of any fatalities or anything along that lines, and it's probably important to note it's still isolated. You know, it's to probably a pretty small percentage of projects, but when it's your project and you have a number of fastener failures, obviously it's a pretty big deal, and then you have to start to question the integrities of the other fasteners that are under similar conditions. So, you know, and again, a lot of these that we've seen, or at least aware of, have been at these steel plate to timber connections, and typically what the ones that most of the ones I'm aware of are kind of these steel collector plates. That's certainly not, you know, which doesn't, you know, it's obviously still serious, but it's not a gravity connection in most of those cases. Obviously, the number of fasteners and the redundancy in those connections also makes a big difference. But I think these are kind of the point of this tech bulletin and this discussion is just kind of to highlight that to everybody so that we could design in a way that limits the risk. I don't know if anybody else has, Felix or Bjorn, if you want to add anything there.
Yeah, and I think, look, the experience that we have as screw manufacturer, that it is really where we've seen these things happening, like Eric said, has been in the steel plates, and oftentimes steel plates that have experienced or where there's been significant moisture. I think that the fastener industry in general is reacting and trying to understand what they can do to minimize the risk, which is things like reducing the hardness of the screws, because that can be done on the manufacturer's side. But I think as designers and installers, we have to be very aware of the fact that even if we do that and we then expose the connection detail to a whole heap of moisture, we could still potentially drive failures there. So we're just trying to, I guess, get ahead of the problem before it turns into a problem, let's say.
Thank you. Does hydrogen embrittlement occur in nails and bolts as well? Should we be looking at designing connections with bolts and dowels or nails instead to prevent this issue?
Well, there has been hydrogen embrittlement in bolts in the past, and that's why certain tests have been incorporated, and that's why manufacturers are onto that, testing coating, testing the bolts, testing the hardness. We designed with bolts. Well, we need the screws and their capacities, their capabilities, their abilities to perform the way they do with the edge distance that we require. So we cannot just replace screws with bolts. I think it's just the nature of the beast. What we need to probably do is incorporate some further testing and some other measures, some QA that is applied to screws in general. So more thorough testing and more thorough restrictions and quality control that is required, but that'll take some time to put into. In the meantime, to reduce that risk is what we're recommending, and basically to evaluate the risk instead.
Yeah, and I agree with that. I guess the only caveat I would add is if there are some connections that you identify as high risk where you think nails could be used and replaced, I think that's fine. You may also choose to use a softer fastener with a more enhanced coating on the screw as well. You could adjust, and there are some proprietary options out there for doing bolted type beam to column connections too, if you so choose. Just be careful that, in often cases, bolted connections don't have the same deformation compatibility in like a seismic situation. So kind of have to evaluate it, holistically in terms of those different connections. But there certainly might be situations where you could get away with nails and have it be a less risky connection.
Is there a way to test on site if there is any reduction in screw capacity due to potential embrittlement?
So that's a difficult question. I think the way you'll see it on site is when the screw heads come off, which then you've gone the wrong way. I mean, I think from an engineering point of view, if you're looking at testing, I would say if you're going to the site and having a look for things like screws that aren't installed straight, so where you can see a misalignment. Look for any damage on the screws that you can see. Look for signs of excessive moisture. You're looking for the causes, I think, rather than the end result.
Yeah,
Eventually, what you could do is you could potentially take those screws, if you see these causes that Felix just highlighted, you take some screws out and send them in to test them for the hardness, for the strength, and then work out if they potentially would fail on tension. But it could lead to delays in a way, but it could be a way to, if you are uncertain and you're concerned, that could be a step to do.
Someone's saying we've seen or heard of more issues with rotoblast screws compared to other manufacturers in Canada. How does the hardness and the IHE of your screws compare to other companies?
So I'd like to answer this because it's really interesting. And I'll take this from you, Felix, because it's probably hard for you to answer. There are actually quite a lot of failures with regards to that. There's a lot of NDAs that are signed, so these problems not openly discussed. But there are failures throughout different suppliers, different manufacturers that are occurring not only in Canada, occurring in Europe, that are occurring in New Zealand. In Canada, as you can see, happened in the past. It might have happened with a rotoblast screw there. I'm not aware of this. Again, this is something really hard to capture at the moment. So the one invitation could be, yes, we have NDAs, but potentially we need to share these, the issues that we observe, under what conditions. We don't need to say which manufacturer or supplier this is, but just to get an awareness of how many screws and where and what conditions they have failed. And I just encourage everyone to potentially even use TDS to report this, to collect them confidentially, and then release some reporting on the risk related to that. So I think it's not only focused on one supplier, and I can only say that to that question. I don't know, Eric, if you wanted to add something to that.
No, I mean, I suppose the one thing would maybe give, I know speaking with Felix and other individuals at Rotoblast that they've made some steps to change their process in the last couple of years. And Felix, in my understanding, is going forward, going to be producing screws in conformance with the Canadian code for the most part. So I mean, I might just hand it to you. I know there's other manufacturers making adjustments as well to get themselves in conformance with these new requirements, but
yeah, look, I'm happy to answer. I don't think, well, I'd be biased, but I don't think there's a difference between us and other suppliers, to be honest. I certainly know of other suppliers that have had the same issues. The IHE side of things, I would say is not the big problem. It's generally well controlled now, and the EHE is really the problem, which is hard to control as a screw manufacturer. So we've been quite vocal now throughout the process, and we're trying to actively look, I guess, for industry solutions. Yeah, sometimes that being vocal means that you get picked on a little bit more than others, but I can't say that it's a Rotorblast issue. It's just an industry issue to work through, and at the end of the day, I wouldn't say it's just a screw manufacturer issue. It's really an issue of how we're constructing things and the general way that we're looking at timber construction, maybe compared to some other construction types.
Yeah, and I'd really encourage discussions with your screw manufacturer to understand what it is you're getting and whether it's going to be in conformance with these new requirements. The boxes don't come with hardness labels on them, so you really do have to ask or specify what you want if you expect to get it on your project.
Great. Well, thank you so much. We've got a few questions left, but I think we were out of time. But this has been a very interesting and great discussion. I think it worked well having all three of you with your slightly different perspectives, and we really appreciate your time and coming all the way from Europe, Bjorn. So thank you very much, everyone, and thanks for joining in, and have a great holiday, and we will see you all in February. Thanks.
Great. Thanks, Emma.